Okay, here's where we left off on Monday of this week. We had an equation in vertex format. Okay. We found the vertex, opposite sign here, same sign. The positive here had it open up. The 3 is our line of symmetry, x equals 3. Okay. We substituted 0 for x to find the y-intercept. Right up here. Now, this part down here is them mathematically finding out the 2 x-intercepts. But in this particular problem, because the y-intercept was 0, and according to the rule of symmetry, same distance, also at y is 0, we got our 2 x-intercepts, and we didn't really need to do the computation on this problem. Now, if the y-intercept were anywhere besides 0, 0, then we would have to do that kind of stuff. Okay? So that brings us to today's problem. When you see this problem, what immediately comes to mind that I've warned you about? The negative in front is going to do what? It's going to make it invert, isn't it? Won't hold water. The cup won't. Okay? Y-intercept, positive 2, negative 1. Okay? Let's go ahead and put that up there. Positive 2, negative 1. Right here is the y-intercept. We know this thing's got to come down this way. So will there be any x-intercepts? Easy for me to say this morning. No, there won't. Now, if you put this equation into the quadratic formula, you would get imaginary numbers. Okay? And that's what happens. Anytime it doesn't cross the x-axis, you get imaginary numbers. Now, let's go on. Okay, the next thing we want to do here is we want to find the y-intercept. So we substitute 0 for x, and we negative 5. So the y-intercept is 1, 2, 3, 4, 5. The point 0, negative 5. Okay. Now, the other thing that we need to remember is because this is over 2 on the vertex, then that means that this is the axis of symmetry. Okay? Because the axis of symmetry always goes through the x value of the vertex. Now, we've got those pieces of information. With that, what I've got on the board right now, we've got enough to graph this equation. Maybe not perfectly, but very close. Okay? What would it look like if we were to graph it? Well, here's our vertex. This thing's going to come down like this, through here, and on down like that. 2 over here, so 2 over there. So this one would come down just exactly the same way. And that's what our graph is going to look like on this equation, without doing any more work. Okay? So did we answer all the questions? Yes, we graphed it. Did we identify the vertex? Yes. Did we find the x and y-intercepts? Well, we found the y-intercept, but there is no x-intercept on this because it's going away from the x-axis. Okay? And the axis of symmetry we also found. What is this? These are the calculations on this. Now, look at this thing. Here they took this equation right here, okay? They moved the 1 over to the other side. This is what you would have to do if it actually did cross. 1 would go on the other side, and once you got this, what you would then have to do is take square root of this and take square root of that plus or minus. In this case, you would get x minus 2 equals plus or minus I, or 1i. Okay? Take the 2 over, x equals 2 plus or minus I. Those would be the x values. Well, we can't graph imaginaries. And the graph didn't go up here. So that's why that works out that way. Any questions on this one before I go on? Okay. In this case, all of this was unnecessary work. Once you've got that vertex, if you see it's below the x-axis and it's going down, you don't need to do this stuff, because it's just a waste of time, basically. As you just simply say, no x-intercept. Okay, so there's their graph, which matches mine awfully closely. Okay, graph the quadratic function, identify the vertex x and y-intercept, same instructions. A little bit different problem. This one's going to go up, right? -2, -1 is going to be the vertex. So -2, 1, 2, -1 is going to be the vertex right there. Okay. Let's find the y-intercept. We're going to replace with 0. So, or in this case, g. Or replace x with 0, so we would have 0 plus 2 squared minus 1 equals 2 squared minus 1 equals 4 minus 1 equals 3. So positive 3, 1, 2, 3, there is the y-intercept. Also, right here, since that's the vertex, then this is the line of symmetry, x equals -2. And now we can graph the thing. This is going to go over here like that. This one's over here like that. 2 places here, 2 places over there. Okay. Which brings up this batch of scribbles that I've previously done. Okay, basically I'm giving you this equation again. Okay, this is the solution to the previous problem. Here's where we replace to get the y-intercept. Same stuff we did before. Okay, so that's the y-intercept. Here's our vertex, same as before. Okay, now, what about these 2 points right here? Since it does say to find the x-intercepts, we need to do this. So I write this I take the one on the other side, square root of both sides plus or minus. Before I had this one on that side, but that doesn't matter. Okay. That gives me the plus side of this equation right here. And that gives me the minus side of this equation over here. So I get x equals -1 for one of my values right there. And x equals -3, 1, 2, 3 for my other one. Okay. So my intercepts are those 2 points. Now, one of the saddest things that came up on your test. On page 3. On page 3, almost half of the class on problem number 10, which asks you to find the x and the y intercepts, only gave me the values of -2 and 6 instead of the points -2, 0 and the point 0, 6. So sad. Remember, if it asks for intercept, it's looking for a point answer. Okay. Well, the good news is the other half of you did it right. So I guess there's celebration and weeping out of different eyes. Well, any questions about this one? We've covered it twice. Here's a different one. Now, here's something new. See this equation right here, which is the one we just did twice. And there it is again. And see this equation in standard form? Those two are the same equation. I'm going to take a moment to show you how to convert back and forth. Okay? So, how did I go from that to this? Well, I took x plus 2 and I squared it, getting x squared plus 4x plus 4. If I square that, x plus 2 times x plus 2, and then I just bring down this -1. So I combine those and I get x squared plus 4x plus 3. That's how I went from vertex to standard. And that's how you do it on all of them. Now, what if I had a 5 out here in front? What if? Or even a -5? Well, you still have to do this first, except you'd have the -5 in front of it. Okay? And down here, you'd have to multiply -5 times all of that. -5x squared plus -20x plus -20 minus 1, because you're not taking that -5 times the -1. And then you have to combine these two and get -21. If there were a -5 out front. The main thing I'm trying to show you here is it goes times this, but not that. Now, I'm going to erase this. Pretty simple to change that to this, isn't it? I'm not quite ready to show you. Well, actually, I am ready. I am ready to show you how to go from this to that. Now, the typical way that they teach you to do that in excuse me, got a frog in my throat. The typical way they try to teach you to do that in most algebra classes is by a process called completing the square. And it's a fairly lengthy process. It's a process that has a lot of dangers in it. Okay? But there's a vastly easier way to do it. The Carter way. Okay? So if we take this equation, there's something you need to know. This little formula right here, x equals negative b over 2a. That is the formula to find the line of symmetry from this style equation. Okay? That's the formula to find the line of symmetry, which is the first step in finding the vertex. It's the x value of the vertex. Okay? Now, what we do in this case is if we do x equals negative b over 2a, then in this case, it's going to be negative 4 over 2 times 1, or negative 2 altogether. Okay? Well, isn't that what we had before? 1, 2. For our line of symmetry. See, that's the same on either. But we don't know the vertex yet because we don't know the y value to go with this. Okay? So how do we find that y value to go with it? We take this negative 2 and we substitute it into here. And I don't think I've got that. Yes, actually, I do have that shown right down here. I'm going to take this negative 2 that I got right here, right there, and I'm going to put it in here where this x is and where that x is. That gives me 4, that gives me negative 8, and I've still got the 3 brought down. And this is cut off. But 4 minus 8 is negative 4 plus 3 is negative 1. Equals negative 1. I don't know what that scribble is. Okay. What that means then is if the x value is 3 and the y value is negative 1, then your vertex is the point negative. Not part of it, that's something else. Then is negative 2, negative 1. That's your vertex. Just like we had before. Now it's a little more work to get the vertex from this format. Okay? But that's how you do it. Now, what about you can still find the y-intercept. How do we find the y-intercept? Well, we replace x with 0. So I would, since I've got this actually duplicated right here, I'm going to erase this. And to find the y-intercept, we replace x with 0. So 0 squared plus 4 times 0 plus 3 equals 3. Or why bother? It's just going to be that one. Always. Because these two are always going to wipe out. Okay? So my y-intercept then, y-intercept is the point 0, 3. And I remembered to put it in point form. Right here. Okay. So we've got enough information to graph this thing. We've got the line of symmetry. We've got the y-intercept. We've got the vertex. We can draw this up through here and up through here. This one's the same amount of space from that one, just like before. But we do need to go ahead and calculate these. What would our calculations look like from this form instead? Well, if we did it from this form, then what we would have to do, and I'm going to work over here, I guess, because I've got space right here, I can do it. I need to find the x-intercepts, or the solutions, or the roots, the points on the x-axis. Now, I know from habit that they're going to be over one, up one, over one, up one there. Okay? Since there's no number immediately times this. Okay? But in this case, I can either factor that thing. Will it factor? Well, yes, it actually will. That thing will factor into x plus 3 times x plus 1 equals 0. Okay? You see those factors? 3 times 1 is 3. 3 plus 1 is 4. Okay? You match the center. If that's true, then this gives me a value of -3, and this one gives me a value of -1. -1, -3. And there's our graph. Okay? So you can totally do it from vertex method, or you can totally do it from this one. This one's a little harder, maybe, because you got to go through this -b/2a distance first. Okay? Now, I want to show you where that -b/2a formula came from. Okay? I want to show you where it came from. In the quadratic formula, x equals -b plus or minus square root of b squared. And by the way, some of you leave off that square. Minus 4ac, everything over 2a. Well, we've had fractions before where we uncommon denominatorialize this thing to make it look like this: -b/2a plus or minus square root of b squared minus 4ac over 2a. That kind of thing. Look at what we've got here. There's that formula. That's where that comes from. In the quadratic formula, this first part of this thing gives you the line of symmetry and the x value of the vertex in the quadratic formula. Okay? So I just wanted to show you that in case you had never seen that before. Have any of you seen that before? No? Well, that's the way the quadratic formula breaks down. And remember, this thing predicts how many values you're going to have, whether you're going to have 1 point, 1 value, 2 values, rational, irrational, whatever the case may be. Okay, well, let's go on. Okay. Find the vertex of a standard form parabola by using the vertex form. You know what? We just did that. We just did that. Now, this is review telling you what if, in this case, A would be negative. In this case, A would be positive. Okay, we've discussed that before. Now, here's that formula we've already used. Okay, and I've shown you where that came from. This is also the equation for the axis of symmetry. And then you substitute the x value, whatever answer you get here, okay, into the equation to get the y value. Now, here's the fancy notation to denote that. So if you want the vertex, technically, here's the notation. In reality, this gives you the x value. This business, which this is a way of saying, I'm going to substitute this x value into the equation. That's what this is saying. This is saying, I'm going to take this x value and I'm going to substitute it, substitution value, into this equation. For example, a moment ago, we got an answer of x equals -2, didn't we? A moment ago. So what this is equivalent of saying is for this value, I would be doing substituting x is -2 into the equation. And over here, this would be -2. Okay. Now, I don't know that it's absolutely important that you memorize this notation as long as you know what to do. You get this, and whatever answer you get up here, you substitute that into the equation to get the y value of the vertex. Okay, that's what's important. Oh, look at this thing. Here's an equation, okay? Actually, that's the same one we had before, wasn't it? Same equation again. Okay, except no, this isn't exactly the same one, it's similar. Similar. Okay, so first thing we're going to do is we're going to do something called determine the n values, since that's what the instructions say. You guys already know that. The n values are if it's a square and it's a positive leading term, it's going to go up and up. If it's a square and it's a negative leading term, it's going to go down and down. We've done that. They want us to do it. So we look at this leading term is a +1. That's a square, so we know this is an upward going quadrilateral or parabola. Okay, now the next things we want to do is we want to find the line of symmetry in the vertex. Okay, what are the steps for that? Use x equals -b/2a to get the x value of the line of symmetry. Then substitute it into that to get, okay, here's my finding the line of symmetry right here at -2. Then I'm going to substitute that -2 into the equation to get, in this case, 0, or the vertex -2, 0. Question about that before I go on. I need to make absolutely sure you understand what I did there. Any questions? No? Okay. Well, so here's my point, -2, 0. There's the vertex. Be nice to know the y-intercept. Okay? So basically, we replace in the equation the 0. Those two are going to wipe out. The y-intercept is going to be the point 0, 4. That's how easy y-intercept is. Right there. And because of symmetry, if this is 2 over, then there's 2 over right there. So this point, what is it? -4, -4, -4, +4 would be the matching point. Okay. Now then, finally, if we want to know where, whoops, Didn't want to do that. Okay. Finally, if we want to know where this thing hits the x-axis, well, in this case, the vertex was on the x-axis. So there's only one point on the x-axis. We don't even need to do any calculation because we figured it out because the vertex is a single point. Okay, so my x-intercepts are simply the point -2, 0 is the only one. Now, I'm going to tell you something that I'll be telling you again a little later, okay? The fact that there's only one of these, okay, and this goes up and that goes up, it's a turning point. In some previous equations, we had it crossing, right? And when it crossed, we typically had 2 points. Well, when there's 1 point, that's called multiplicity, even multiplicity. When there's 2 points that cross, that's called odd multiplicity. That's previews of some coming distractions. Okay? And it'll make more sense a little later, I think, I hope. Oh my goodness. Look at this thing. Kind of nasty, right? Well, there it is. Actually, it wasn't nearly as nasty as you might have thought, because we don't get that involved on finding this x value. But now we do get it involved in finding the y value. So we take this 8 and we substitute it into that nasty equation. And we get a y value of 27. So in this case, my vertex is the point 8, 27. All right, looking at this. Now, what I did here, or what they did here, is they converted this into vertex form. Now look at this. This is the second part of what I previewed earlier. Look at this. If A is -3 here, A is -3 here. It's just a bring down. Okay, from our vertex, we got this number opposite of sign, and we got this number opposite, this number same of sign. Okay, so that's how you convert these fully to those. When I did it before, our A was a 1 in the previous case. But you need to know that if A is something different than 1 up here, the A will still be that down here. And if we multiplied this thing out, it would go back to that. Okay, I don't want to take the time to do it, but it would. Well, here's another one. -x² plus 6x minus 8. I find the line of symmetry, x equals 3. Okay. Now, I plug in that 3, and I get 7 for the y value, so my vertex is 3, 7. So here we go, 1, 2, 3, and up 7. There's my vertex, and there is my line of symmetry. Next thing I'm going to do is I'm going to find the y-intercept. Okay, what's the y-intercept going to be on this thing? Well, we're going to substitute a 0 there, and our answer is going to be -8. So here, -8 is the y-intercept. And if this is 3 over, that's 3 over. That gives us another graphing point. The only other thing we need to do on this problem, since it does cross the x-axis, is we've got to solve for the x values. What are our tools from that format? Our tools from that format are factor, quadratic equation. Okay, either way will work. Now, in this case, this thing factors into this. Or I could factor the -1 out of that if I wanted to. Make it -1, positive x, -2. Okay? In either case, my two values are 4 and 2. Here is the 2, here is the 4. And we've done everything we need to do. Oh, here, ending terms, negative, this thing's going to go, and second degree, this thing's going to go down and down. Well, we're not going to work that one. We're going to skip over that one. I just want to show you this. This is not accountable. Okay. A quarterback, Mahomes, throws a football with an initial velocity of 72 feet per second and an angle of 25 degrees. Okay, here's 0 degrees. There's 45 degrees, so about right here is about 25 degrees. Now, that's about the angle that Mahomes typically throws maybe a 30-yard pass. Okay, now if he's throwing a Hail Mary from one end of the field to the other, he throws it a little higher. Okay. Now, anyway, we go on, and this +5 right here, Mahomes didn't throw it from the ground. Mahomes threw it 5 feet above the ground. And that's why our graph starts here at +5. Remember our transformations, it moves it up 5. Okay. Our y-intercept. Okay. Well, he throws this thing at this 25-degree angle, and what goes up must come down. And anytime you see a 6t squared or a 32t squared, that is a gravity problem. Whether it's rockets in the movie, not the sky, October Sky, about the kids in the science fair, that's basically the formula that kid used. A slight variation of that to find where his rocket really went. Now, what else does it say? How far does it go until Kelsey catches it 3 feet above the ground? Wasn't that kind of cool? They put him in defense in the last play of the last game. You know what the strategy was? They didn't want a defender. They wanted a receiver for Kelsey to intercept the ball if it came. Okay, because it's so big, I mean, he's like 6'3" and has such wonderful hands. Nothing to, well, anyway, I digress. But that's what this problem about. You can work this kind of stuff up. What is the x-axis? It's actually in time. How long the ball is in the air is what that x-axis value is telling you in this case. Well, let's go on. Polynomials. Now I can't say it for real. Polynomials. Okay. Well, let's look. Oh goodness. We've already talked about in behavior, but I'll run through this real quickly. Okay, first of all, let's describe what I'm talking about. Don't copy this down. Don't copy this down, okay? It makes you crazy. Well, probably all of this does. But This is a general standard form polynomial of I don't know what degree. Okay. Now, here's an example put into this particular example. Okay. In this particular example, if it were fourth degree, the n here would represent this, and this a sub n would represent whatever number is up here. Okay, whatever number. Now, for this notation, we move back one place, 1 degree. We get 1 degree smaller. That's why we have n minus 1, is because this one is 1 degree smaller than that one. Well, the easy way to think about this means it's just one place back. Okay, which would give you the 4. This -2 is 2 places back. Okay, and this one is however many places back, and that one's however many places back. Okay, and it goes back there. Here you see we've dropped 2 degrees. You see the general format of how these work? Hopefully, you aren't looking certain.
No.
You-
No, I'm good.
Oh, okay. Now, you've all heard of bicycles. Binomial, 2 terms. Tricycles, trinomial, 3 terms. A quadruped, 4 on the ground, 4 terms. I mean, you could call it a quintinomial and a septinomial and a septinomial and octinomial, and you could go to oblivion on that, but we don't. After it gets higher than a trinomial, we just call them polynomials, which means many terms, just like Polynesian means many islands. Okay. So that's the idea on here. And as you see here, this is the first coefficient. The number in front of a variable is called the coefficient. This one is 1 back, or the second coefficient, and so on. Okay, and so that's the general leading term. Okay, if it's an even power, and a positive first term, we've talked about this already. It's going to go up and up. Here's an example of what might be a W6. Here's a W squared, a parabola. Here's a W to the 4th, might look like that. If you draw the axis through here, 1, 2, 3, 4 crossing points. 1, 2, 3, 4. In this case, you can have as many, but you can have fewer crossing points or touching points. Okay. Well, what about over here? What if A is a negative number? Well, then you're going to go down and down. Okay, inverted cup. What would a 4th degree one look like that? What would a 6th degree maybe like that? Okay. Basically here you're saying, even though they may be imaginary, you got 2x values there, 2x there, and 2x values there. You're saying on this. Potential, even some may be imaginary. Okay, now, here's just another look at the same thing from a technical point of view. This is saying as x approaches negative infinity, the whole thing, the whole equation is going to positive infinity. In other words, this is going to that infinity, this one's going to this infinity, both up and down, or up and sideways, I should say. And the corresponding difference on that. I don't know that this business about infinity is worth writing down. Okay, I don't know that it is. And there's another one. This time we're dealing with odd degree ones. Here's the general odd shape. third, fifth, seventh, ninth power. Okay. Basically goes from down to up. Kind of like this. Or if you got a negative first term, it'll go from up to down. And that's kind of like that. And that's just the end behavior on those. Okay. Now, whether it's I know we're talking about odd powers, whether it's a second or a third or a fifth or a seventh or a ninth, just would put more bumps in it, potentially. Okay, what about this one? What's the end behavior of this one gonna be? It's gonna probably go like that. Okay. Start low and go high. Start low and end up high. What about this one? Well, we got to figure out what the total degree of this thing is. In this one, the total degree, there's a hidden 1 power right here, right? So that means that this is going to be an x to the first. This is a 3, so this means x plus 1 times x plus 1 times x plus 1, which would give us an x cubed. So we would be taking an x cubed times an x to the first. So the total degree of this thing, whoops, is 4. Okay, see how you count the total degrees? Which is an even number. And whether it's an even or odd, it will become important in just a moment. Okay. Well, that -2 is also going to be the a term. Again, when we multiply these stuff out, then times -2, the a term is going to be that. So what do we know about how this graph is going to look? It's going to be down and down, and it may have some bumps like my knuckles. Okay. Okay, here just some more that we can kind of go through that. Highest degree on this is 4. Leading term is negative, so that one's down and down. This one, 4, 6, 7. You see I'm counting those degrees. 4, 6, 7. If we had this all multiplied out. So in that case, we're going to have one of these kind of, I can't do that with my fingers. They don't work. The general form is, whoops, I hit backwards again. The general form for that one is going to be like that. Whoops. Yeah, it's positive first term. So it'll be something like this. Since it's 7th degree, it'll probably have one, 2, 3, 4, 5, 6. It could be like that. Now, I don't know that it will, but I mean, I know that it won't. And we'll get into some more particular graphing things in the future to show you that. Fact is, I'll show you that right now. You've got +9. You've got +4. Agreed? 1 2/3 is almost 2. Here would be 2, so right there would be 1 2/3. Or 5/3. Now, this particular graph, I only have 3 points. These 4 of these right here, when that's an even power, that's called what we call multiplicity even. And instead of being a crossing line, it's a touch and go. Okay. So if I wanted to know literally what this graph looked like, and I'm not going to worry about this 6/7 right at the moment, because that would affect the steepness, make it spread out a little wider. But basically, if this has a total of 4 6 7 power, 7th degree, then I know that this thing has to start low, and I know that this thing has to end high. And in very loose terms, that means this is going to come up, come down here and touch. And then a touch here, because that's an even multiplicity. This is an even multiplicity, meaning another touch and go. This one is a first power, an odd multiplicity. Okay. So that's why it is a crossing one. So if you have an odd power behind a factor, the graph is going to cross the x-axis. If you have an even power behind a factor, then it's going to touch and go. This is a pretty realistic graph of that equation. Okay. Now, I don't know how high these two go without doing some XY point plot. Okay. Here, between 4 and 5, halfway there is 6, roughly. So I'd try substituting in x equals 6 and see what y was. Between this one and this one, I'd probably try 3 and see how high it goes to get an idea realistically of how high that loop is. But anyway, that's kind of what we could figure out the y-intercept by putting 0 here, here, and here. Okay. This one would be, I'd have 9 to the 4th power times 16 times 25 times 6/7. So the y-intercept on this thing is probably going to be way down here somewhere. Well, anyhow, that's multiplicity. Now I'm going to hit that some more, but I wanted to make sure that I had hit it this morning. Look what's coming up. Multiplicity. Okay, let's look through this. The value is x in the domain. What is the domain? It's the set of possible x values, right? The set of possible substitute values. Where y equals 0 are called the roots of the function or the solutions or the zeros. These 3 words all mean the same thing. This business of talking about y equals 0 just means it has to be points on the x-axis. Because on the x-axis, y is 0. That's why that's in there. That's actually kind of a disclaimer. Okay, or a restriction. Now, let's look at this. Those could all be factors of a problem if you factored it. Okay, kind of like in that previous problem up back here. This is a factored equation, is what that is. Of course, this one is unfactored, but that one is a factored equation. So when I'm talking about factors, I'm talking about the pieces that would factor out and multiply times each other. Whoops, too fast. Okay, now, this factor, if you just got an x, it'll be 0. Well, 0 squared is still 0. If you got an x minus 3, you'll get x equals 3. And we talked about going from factor to solution, solution to factor before. If x is 2, then, if the factor is x plus 2, then we get a negative 2, and so on. So we can I can give you a factored problem, or I can give you an unfactored problem. If I give you a factored one, it's easy, because right there's the solutions already. Now, let's go on. Here's a problem that's not factored. Third degree. Can't use the quadratic, can't use normal factoring, but we can factor by grouping. We've done that before. It was on your factoring sheet, in fact. So I'm going to divide it into those two pieces right here. Those two pieces, okay? Here, I factored it out an x squared, leaving x minus 5. Here, I factored out a negative 16, leaving x minus 5. The same thing. Okay? Now, since I've got the same thing right here, I can let my garbage truck pick it up. Well, I've got this slide's going to bring it down, so I don't need to write it. Okay, here's that common factor here, and here's what's left as a factor. And it equals 0, of course. So we got those two, except this still needs to be factored more. And this one's going to be easy because it's a conjugate. Perfect square on the front, perfect square on the back, minus in the middle. Well, this gives us a value of 5. And that gives me a value of plus or minus 4. Okay. Now, they showed it this way, in which case they would have done this, or you could have done it that way. And either of this way or that way is okay. So anyway, we've got that value of plus or minus 4 and 5. This 5 and those two 4s, plus or minus, are the solutions, or the zeros, or the roots of this equation. What does that mean? Okay, here is 5. Here's positive 4. There's negative 4. That means this graph has got to go through those 3 points, or at least touch those 3 points. Now, if we looked at the factors, remember I'm replacing this with x minus 4, x plus 4. All of these factors are odd-powered factors, aren't they? That means that all 3 of these are odd multiplicity. That means all 3 of these are crossing lines. Okay? Well, what's the total degree? 3. So this thing's got to end that way and got to end that way, because it's a positive. What's it going to do in the middle? Well, it's going to come up something like this. You go down something like that, and then come back up something like this. Okay? Because all 3 of these have to be crossing, because First power, first power, first power. Okay. Now, there's one more piece of information on this problem that we could get that would help us to know the exact shape of this. There's your y-intercept. Way up here. So that means that this thing's got to go up here and back down pretty steeply. Okay. Now, how could we find out how deep this one goes if we wanted to? If we wanted to. Okay, well, how we could? This is 4, that's 6, right? Let's substitute 5 into that equation and see what value we would get. Okay, and I'm not going to do it because I don't want to take the time. Most of the time, if you can tell me the y-intercept, you can tell me the x-intercepts, the roots, the zeros, the solutions. If you can tell me those, then use that ending thing. You can get a graph that's good enough. Most of the time, I'm not going to care just exactly how long this minimum goes down. Okay? Now, I cared about this one because it happened to be the y-intercept. Because those two were the same distance apart. And usually it's going to be close to symmetric between these two and between those two. Not always, not exactly, but close enough for a sketch graph. Okay? Questions on this before I erase it? Need to erase that too. And a little bit more. Well, now let's formally talk about multiplicity, now that I've been talking about it. Okay, this just says if you got some factor, x either plus or minus some number, okay, x minus 3, x plus 4, whatever. We look at whatever power is on that factor when we're determining multiplicity. Now, in this case, if I had those three multiplied together, I've got commas. I really shouldn't have put those commas there because I really intended for them to multiply together. This morning about 4:30. I woke up early and couldn't go back to sleep. So I got ambitious. What is my total multiplicity? 1, 3 makes 4. Or what is my total degree? 4 and 5 is 9, so my total degree is 9. So for the whole thing, I have an odd multiplicity. But let's look at each individual piece. Is this going to cross or touch and go? Is this going to cross or just turn? This one's going to cross because it's odd. This one's going to cross because it's odd. This one's going to cross because it's odd. These are just examples of odd multiplicity. I've got a even one, even one, even one. That means that all of these would be touch and go points. Come down, touch the x-axis, and turn back. Okay? Or turning points is what Alex is going to call them. Okay? Now, if we wanted to know end behavior, 2, 6, 12. Up and up, because there's no negatives, no negative A's. Okay? Okay, we got the red and we got the green. What are we going to do here? with this, that's a first power, so that's an odd multiplicity. It's going to cross. 3, that's an odd multiplicity. It's going to cross. And there's another x cubed, which is a third. That's another x. That's another crossing. What these are saying is if you got even powers, then it's going to turn and go back the way it came. Or it's still getting going towards infinity. Okay, let's look at this. This is a factored equation. This is a factored equation. We've got an x to the first here. We've got a second power and a third power. This is going to give us an x value of 0, the value we graph. This one's going to give us a value to graph of 1. This one's going to give us a value to graph of -3. Now, that is a multiplicity 1, means that that's going to be a crossing point. This multiplicity of 2 is going to be a touch and go point. This multiplicity of 3 is going to be a crossing point. Let's see what I'm talking about. Graph paper. Points 0, 1, and -3. Okay, we said that this one is going to be a crossing point. We said that this one is going to be a touch and go point. Either this way or that way, we don't know yet. This one, we said, is going to be a crossing point. Okay, now, what's the total degree of this thing? So we can get our ending values. 1, 3, 6. So the total degree is 6. That means we're going to have that. For the graph. On the graph, since this is on one end, that means this one's got to go up and cross the line. This one has to end up. But it's not going to cross the line because it has a touch and go multiplicity of even. So what do we do between here and here? Well, that means this one's going to come up here and down like this and back like that. Okay. So that's what that would mean. And this would be a reasonable graph for that problem. Question? Anybody? Well, in this case, the answer was just find the zeros. Well, here, here, and here. Okay, and their multiplicities here, here, and here. I just took this farther than we would have. Not based on what that said right up there. Okay. Here's another problem. We got a multiplicity of 2, a touch and go point, a crossing point, a touch and go point, a crossing point. Okay. What would this one look like? Well, graph paper. That would give me a 0. That would give me a +3. That would give me a +2. that would give me, excuse me, that would give me a -2. And this would give me a +1. Okay, so I have 4 points here. Let's look at the total degree. 2, 3, 4, 5, 6, 7, 8. Even. That means that this one's got to go up and that one's got to go up. Okay, so we got these. This one, the 2, or -2 rather, is a touch and go. That means this has got to come back up this way some far and then back to here. The 0 is also a touch and go because it's an even power. So it's got to go back up again and come down. But the 1 is a crossing power. Excuse me, not the 1, the 3. The 3 is a crossing. Wait a minute. Okay, here is the 0 touching, 3 crossing, 2 -2 touch and go, +1 crossing is the way these have got to go. And the total powers of 8, those are correct. Now let me rethink this. Okay, so I've got the farthest left one happens to be this -2, and it is a touch and go. So I correctly did that. Okay. The next one, the 0, is also a touch and go. So that means this one's going to do that. I did that right. Then the next one is the +1, which is a crossing. So it turns, crosses, and then comes up this way. So that's generally what that graph is going to look like. Okay. Okay, this is just more of what we've done. We've got a 0 there, we got a 1 there, we've got a -3 here. Total degree 1, 2, 3, low to high. Okay, and you get that, and I can tell you guys are itching to get out of here. Goodbye. Don't come back.